Hello guys, welcome back to another awesome video with Learning with Satvik. Today we have a special request from some of my classmates to do a test review for Unit 6 of Honors Chemistry. So let's begin. The first question gives the following ionization energies, and it's asking to find an element that fits the description, that is in row 4. So how this works is that whenever there is a big jump, that is how many valence electrons there are. So, to elaborate, we see here that the ionization energies are 700, 1200, 1350, 1900, 6700, and 7100. So, we see that the biggest noticeable jump is between 1900 to 6700. So, when looking at it, this is level 1, 2, 3, and this would be 4. So, because that's 4, that would mean that the element that's being described has 4 valence electrons. So next we are given that it's in row 4. So we can see here 1, 2, 3, 4. So this right here would be our row 4. So then the easiest way that I find to find the valence electrons is by simply just counting from left to right. So potassium would have 1, calcium would have 2 valence electrons, Ga would have 3, and then Ge, germanium, would have 4 valence electrons. So the answer to this problem would just be Ge, because it is in row 4 and it has 4 valence electrons. And again, just to recap, we got this number 4 because the jump in ionization energies is from 1900 to 6700. Okay. This next problem here asks to calculate the Z effective of Cl, or chlorine. So let's begin. So we are first given, obviously, that Cl is 17, so plus 17. And then because it's not an ion, it's a neutral atom, we do not have to eliminate any other elements. So because we immediately know it's 17, we know that it would be in the 1, 2, 3. It's in the third energy level because of this 3s2 right here. These are the s's, and then this would be 1, 2, 3. So 3s level. So that means that the valence electrons are located in the third orbital. So we put the 3 in the top left. Next, we're trying to basically block out any electrons that are blocking chlorine right here. How I like to think of this is if you're seated in a concert, it's whoever is in front of you. So going based on that, we see that neon here is in energy level 2. The valence electrons are in energy level 2. So, which is why we subtract 17 minus 10. So then after we see neon, then we go through Na and Mg. And these are in level 3. So going back to the concert analogy, these elements, if you think about it, are next to our chlorine. So are they blocking the view to the singer? No. So that's why we do not eliminate them. Next, we look at Al, Si, P, and S. They again are all in the same view, or in the same level, so they do not block the view. And then Cl also is the same thing. So 17 minus 10 would get us plus 7 as our final answer. And just a way to double check for these neutral elements, minus the inner transition elements over here, we can just count by saying group 1, 2, 3, 4, 5, 6, 7, and 8. So by just looking at these groups here for neutral elements, we would be able to see what the Z effective is. So only for neutral elements. So because chlorine here is in group 7, we know that since it's neutral, it would have a Z effective as plus 7. So still write out these steps for neutral elements, but this is just an easy way to check to make sure that your answer is correct for neutral elements. Okay, moving on, we're tasked with finding the Z effective of Pu+. So where is Pu? Pu is right here in element 94. So we can immediately write this Pu plus as plus 94. So then we have to see, because it's positive, we're going to want to eliminate one of the valence electrons. So by doing this, we can see that it's 94. So the valence electrons in the highest orbital level would be one of these, Fr or Ra. So I'll just go ahead and eliminate 88 or Ra. So next, because we only eliminated one of these elements in the 7th orbital, we still have one more left, or in this case, francium. So we would just say that Pu is in the 7th orbital because we still have Fr, which is in the 7th orbital. So now we have to eliminate any elements that are blocking the view yet again. So what element here is blocking the view of a 7th energy level element? That would indeed be radon, Rn, which is 86. So we would do plus 94 minus 86. Next, we have to see after radon, Fr is not blocking it because it's 7th level. Rn we eliminated. And then going on to 89, 89 would be in the 6th level, 6D1. So that is indeed blocking the view. So we would do minus 1. After that, we have to look at the 90 element right there. And then these are all in the 5F orbital. So 5 is less than the 7th energy level. So these would be blocking. So counting that out, that would be 1, 2, 3, 4, 5. We would always want to count this element that we are doing. Because if you think about it, the valence electron for this Pu positive is in the 7th orbital. And right here, this is in the 5F orbital. So it still is blocking it. So because we counted out 5, we would do minus 5. So then if we just grab our calculator here, we can just do 94 minus 86 minus 1 minus 5. And that would give us our answer as plus 2 for the Z effective. Okay, moving on, we have another Z effective question, this time for BH plus 4, or borium. So BH plus 4 is right here, number 107. So we can go ahead and write that as plus 107. So now we have to eliminate 4 different elements, or 4 valence electrons. So the very first 2 obvious valence electrons would be right here, Fr and Ra, which are in the 7s2 orbital. And we would just eliminate those because those are the outermost electrons for this specific ion. Next, we would want to eliminate any level 6 elements. For these type of problems, when calculating Z effective, it doesn't necessarily matter which level 6 electrons you eliminate. So I would just go ahead and eliminate 107 and 106, just for simplicity's sake. And these are again in the 6D orbital, so that still is a level 6. So now what we have to do is we see that this BH plus 4 is still in a level 6 orbital. So we would write that in the top left. Next, we would want to try and eliminate a level 6. So how might we be able to do that? We can look at this xenon right here, which is level 5. So because it's level 5, again, thinking about it like a concert, it would be blocking. So then we would do minus 54 because that xenon is in level 5. So after that, we would want to look at 55 and then 56. Are they blocking it? No, they are not blocking it because they are in orbital level 6s. And again, going back to the analogy of a concert, they are seated next to our borium right here. So no, they are not blocking the view of the singer. So we just go past those. Then we would want to look at 57. Is that blocking it? Yes, it is blocking it because it's in the 5d orbital. So we would do -1. After that, we would move down to the 58. That 58 is in 4f. The 4 orbital is lower than the 6 orbital that we have here for the valence electrons. So we would subtract all of the elements that are in this 4f. So that would be -14. Because if you count these all out, there are 14 total elements. So then after that, we would go on to our 72. 72, 73, 74, 75, 76, 77, 78, 79, and 80 are all in the 5d orbital. So we would do -9, because if you count that out, that would be 9, excluding that LA that we already did before. So then afterwards, we would go on to this 81st element here. Would we subtract it? And the answer is no, because this is in the 6p orbital, all of these. So again, it would be next to the the borium in a concert, so it's not blocking. After that, we would move down to the 87 and 88, which we had already blocked out or eliminated. Next, we move on to 89. So 89 is in the 6d orbital. So no, that's not blocking it out, so we do not subtract. Afterwards, we look at 5f, which is where element 90 is. So because this is level 5, that's lower than energy level 6, the 6th orbital, we would want to eliminate all of the elements here, which are 14 elements. So we would again do -14. Because again, this is a lower level than the 6 that we have for the borium. So after that, we would look at the 104, and we see that that's in orbital 6d. So we do not eliminate that. Same for 105, and then 106 and 107 we had already eliminated. So then we would just plug into our calculator. 107 minus 54 minus 1 minus 14 minus 9, and then minus 14 again would sum out to be plus 15 as our z effective. Okay, for this next problem, we are asked to place the following elements in increasing order of size. Okay, so the general rule for this is that whenever we have a periodic table like this, the trend goes upwards like this, with the largest elements being down here and the smallest elements being down here, up here. This is the general trend, of course, so not every single element applies to it, but for our test, the general trend will be the only one that's applied. Okay, so by looking at this trend and seeing that the smallest elements are at the very top here, we can just write smallest to largest, and we can see that the smallest one here would be the NE, because it's in the most top right position. So we would just write NE and then just cross that off. Next, we would want to see what's the next one that's over on the top right most. So we would scan, 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 and we would see, oh, SB is pretty right, on the far right. So we would do SB as our next one. After that, we would keep scanning, 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 scan, 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 and we can see, oh, BI. Since BI is directly under it and following the trend, that would mean that it's larger. So we would write BI and then cross that out. After that, we would keep scanning, 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 go all the way here, keep looking, and then we would see, oh, BA. Since BA is the next one that's to the left, it's larger. So we would write BA. And then the final element right next to it, 55, since it's even more left than BA, it's larger, following this general trend. So we would write that as CS right there. So that would be our final answer for going smallest to largest. Okay, for this next problem, we are asked to place the following in increasing order of size. Okay, so because it's increasing, that would be smallest. But what is different about this problem is that these are all isoelectronic, which means that they all have the same number of electrons. So moving forward, when looking at our krypton, which is our only neutral element, we see that it has 36 electrons. Therefore, all of these elements here would also have 36 electrons. So the easiest way to organize these would just be whichever has the highest amount of protons being the smallest to whichever has the least amount of protons is the largest. So when looking at it, we see that SR would have our most amount of protons at 38, so that would be our smallest one. Next, we see that KR would have our next largest amount of protons, so it would be the next smallest at right there. And then we can just eliminate those two as well. The next smallest that we'd see is BR, because it has 35 protons. And then finally, we would be left with Se minus 2, which has 34 protons. So again, the easiest way is just to organize them by the amount of protons. So that would be our final answer for going from smallest to largest for this isoelectronic problem. Okay, moving on, we have general trend problems. So I just listed out here some of the, or all of the trends that you were going to need to know. So the first one right here is water, or H2O, plus any active metal will produce a metal hydroxide plus hydrogen. And it's also important to note that it's always going to be 2 hydrogens there. Okay, so for this these type of problems, we're going to be asked in the form of water plus sodium. He's not going to directly just give us the, like Na. We're going to have to know what that is. Okay, so H2O plus sodium can also just be written as H2O plus Na. So what would that produce? That would produce a metal hydroxide. So that would be NaOH plus H2, or 2 hydrogens. So then with balancing this, we can see that we have 2 hydrogens here, 3 hydrogens here. We have 1 oxygen here, 1 oxygen here, and 1 Na there, and then 1 Na here. So the easiest way to do this would just be to do, I'll get another color here, would be to do 1 over 2 on the right side. So that way all of the hydrogens would equal up. So what that would just equal would be 2H2O plus 2Na plus 2NaOH plus H2. And why I did that is because it's 1/2 here. So you multiply every single term here by 2. Okay, for this next one here, the second trend, it's water plus a metal oxide equals a metal hydroxide. So again, H2O plus sodium oxide would just, again, be H2O plus Na2O. And again, it's Na2O because when looking at our periodic table, Na over here would have a charge of +1, and then oxygen has a charge of -2. So because it is an ionic bond, we would need 2 of these to balance with the 1 oxygen, to have a +2 charge and then a -2 charge. And then that would produce a metal hydroxide. So in this case, the metal that is here is Na, and then hydroxide is just OH. So how can we balance this? It would just to be put a 2 over here. And then it's balanced on both sides. And then going back really quickly to number 1, it's important to note that these active metals are always going to be in group 1A. So these are just the group 1 elements as seen over here. Any of these can be considered, except for hydrogen, can be considered the active metals. So Li, Na, K, Rb, Cs, and then Fr. Any of those can be considered as the active metals for this first trend right here. Okay, so the third trend that we have is H2O plus a metal hydride equals metal hydroxide plus, again, the hydrogens. So what that means is this H2O plus sodium hydride, which again can be written as H2O plus NaH. So this hydride here just means that it has an H. And again, because it's an ionic bond, we would need a charge of 1 of the Na plus 1 with the hydrogen minus 1. So that's already fine how it is. So then that would just equal a metal hydroxide. So that would be NaOH plus H2. H2. And then how might we balance this? It's already balanced. Exactly, which is what you probably were thinking. So we for these type of trends, for this trend 3, we do not have to do any balancing. And then the final one, number 4, is any H2O plus a non-metal oxide produces an oxyacid. So this one here is just a tad bit more laborious. And that is because we would have to write out all of the oxyacids that correspond with the non-metal that we have. So again, writing it out, that would be H2O plus dichlorine pentaoxide. So again, we would be given our molecule in this type of, like written like this, and we would have to write it down into something like Cl2O5. We're not going to directly be given the Cl2O5. And then that produces an oxyacid. So what exactly is an oxyacid? So it's going to be any of the polyatomic ions that we have in our green folder in the sheet, any of those that have an oxygen and are considered oxyacids. So with that being said, for Cl2O5, we would need an oxyacid that has chlorine. So what might these oxyacids be? That would be HClO4, HClO3, HClO2, and then finally HClO. So all of these are our oxyacids that can be used to solve this type of problem because they have the needed chlorine and obviously oxygen because they're oxyacids. Okay, so for these type of problems, we're going to need to go through our oxy numbers, and we would want to do this one here first. That is because whatever the oxy number would be for this chlorine, that would have to match with any one of these oxyacids here on the right. Okay, it'll probably make a little more sense when I go through the problem. I know that's sounded very complicated there. Sorry. So our oxygen, we know that it usually has a oxyacid of -2. So -2 times 5 would just be -10. So then, because it's -10 and these have to be equal, then we know that this would have to be +10. So because that's +10, that would mean that the chlorine here, since there's 2 of them, would equal +5. So basically, we're looking for a element here, or in our oxyacids here, where the chlorine has an oxyacid of +5. Okay, so let's do that. So first for ClO4, we know that O4 is usually -2, and then minus 2 times 4, because there are those 4 oxygens over there, would equal to minus 8. So then, we know that the ClO4 has a charge of minus 1. So that would mean that the Cl has to be plus 7, because it would have to be plus 7 minus 8 to equal minus for this ClO4's charge. So because it's plus 7, that means that the Cl will be plus 7, and then the H hydrogen has a charge of plus 1. So no, this plus 7 does not equal to the plus 5 that we had here for the Cl2. Next, we can move on to the HClO3. Again, ClO3 has a charge of C of negative, similar to that ClO4. So we would just write again our oxygen as negative 2. Negative 2 times 3 would equal to negative 6. And then because it needs to be negative 1, that would be Cl is plus 5. Plus 5, and then hydrogen is plus 1. So this would probably be the one that matches, the oxyacid that matches. But I'm just going to anyways do the other ones as well, just to double check our work. So if it's O2, it's minus 2, minus 4. This would be plus 3, again, because the charge would be minus for the minus. And then for HClO, similarly minus 2, and then minus 2. And then that would mean that this has to be plus 1, because the charge, again, would be minus. So the one that worked out for us, I'll put it in a nice purple color, why not, would be the HClO3. So I would just rewrite this as H2O plus Cl2O5 equals to HClO3. And then we can also never ever forget the balancing here. So what would that be? The easiest way is just 2 on the right side there, so that way the hydrogens, oxygens, and the chlorines all bond with each other. Balance with each other, not bond. Okay. And then one important thing to also note is that for oxyacids like this, because they have this oxygen here, the trend is that when lowering the oxygen count by 1, the charge of whatever other element it is will also reduce by minus 2. So basically what that means is that if I have HClO4, we saw that the chlorine's charge would be plus 7. But then looking at HClO3, it's plus 5. Because the oxygen count reduced by 1, and then the Cl, the oxyacid, all lowered by minus 2. So that's just an easy way also to just double check your work and make sure that you're doing everything correctly. Okay, well that wraps up our review video. So please let me know if you have any other questions or suggestions, and I'd be happy to look over them. I'm Satvik Kolar, and I'm out. Thank you for watching.